This is an exercise about time reversal symmetry. It starts from the following observation, that is, namely, if you calculate a band diagram of a periodic structure, so where you have k on this axis and omega on that axis, that there's always some sort of symmetry going on if you plot your band diagrams, namely that you can flip this diagram along the vertical axis here. So the question is, what causes this symmetry? Why is it the case that if you have a solution for a certain omega k pair, that you automatically also have a solution for omega minus k? Now, at first, you might be tempted to think, okay, in this diagram, there's some sort of mirror symmetry or inversion symmetry. This probably means that there's also a similar mirror or inversion symmetry at work in the actual structure, and that is what causes the symmetry in the band diagram. But that's actually not true, because even if you have a periodic structure, for example, this funny structure that looks like this, which is periodic, where you don't have inversion or mirror symmetry, even in that case, it's always true that if you have a solution for omega k, that you also have a solution for omega minus k. And this has nothing to do with the spatial symmetry. So the question is, where does this come from? And this actually turns out to be related to time reversal symmetry. Now, to make sure we understand why that's the case, why that's plausible, let's take this step by step. And for our first step, let's have a look at the following situation where we're dealing with lossless structures. So epsilon is real. And we're starting from a field which is an eigenfunction of our operator. It's an eigenfunction and it has as eigenvalue lambda omega squared mu. Now the question is, can you show that also H complex conjugate is an eigenfunction of that same operator? And what is the corresponding eigenvalue related to that new solution? So pause the video and see if you can figure this one out for yourself. So we start from the observation that H is an eigenfunction of our Maxwell operator. The Maxwell operator, remember, is curl 1 over epsilon curl. So we have curl 1 over epsilon curl H is equal to omega squared mu of H. And now we need to figure out what happens when we replace H by the complex conjugate of H. So obviously the thing to do is take this entire expression and take the complex conjugate of that expression and then see which parts we need to change and which parts we don't need to change. Let's have a look first at this curl operator. Now that's just a bunch of partial derivatives. If you take the complex conjugate, that doesn't change. So this curl just stays where it is. Then we have epsilon. If we take the complex conjugate of epsilon, since we're dealing with lossless structures and epsilon is therefore real, that also doesn't change. So the only thing we need to change in the left-hand side is just adding a complex conjugate sign to H there. Then let's have a look at omega squared mu. For physical reasons, this is real, but also mathematically speaking, since this is the eigenvalue of a Hermitian eigenvalue problem, this is real, and therefore if you take the complex conjugate, that doesn't change either. So the only thing that you need to add the star to is again H. So what we end up with is basically, if you have that operator and it operates on H star, you also get H star multiplied with a certain number. So therefore H star is also an eigenvalue, an eigenfunction of our operator here. And if you look at the eigenvalue, it's actually the same eigenvalue as the original function. Good, that's interesting, and it hints a little bit at what's going on, but not entirely, because the question is, how should we interpret the complex conjugate of a certain solution? And this is where the next part kicks in. So in the next part, we're going to look at a Phasor representation. So if we have a certain field in the frequency domain, so H in the time domain, it looks cosine omega t plus phi. If we translate that to the frequency domain, to the Phasor domain, remember we can associate a complex number to that, H tilde. If we now do time inversion. So time inversion basically means that we replace t by minus t, so cosine minus omega t plus phi. From basic physics, we know that that should also be a solution to Maxwell's equations, because if we replace t by minus t, we just have a movie that we play back in time. So Maxwell's equations don't make a distinction between forward propagating time and backward propagating time. So if we apply that symmetry to a solution of Maxwell's equations by replacing t by minus t, the question is then, what is the phasor associated to that particular field? So pause the video and see if you can think of the correct answer. So let's start from what we know. We know that h tilde is the phasor corresponding to this time dependence. So this actually means that if we have our phasor h tilde and we multiply it by our choice of time dependence, which is exponential j omega t, and we take the real part, that there the result should be h cosine omega t plus phi. So this is what we know, and this also allows us to very easily figure out what h tilde actually is. Namely, it should be that amplitude h, and then in terms of phase, it's the phase of the oscillation, so exponential j phi. Okay. So this is what we know, and this is how we should calculate the phasor h tilde corresponding to our oscillation here. Good. Now, next thing to figure out is what is the complex number that's associated to this particular time dependence. And a bit inspired by what we were doing here, let's just try and figure out if it's indeed the case that if we take the complex conjugate of that phasor, that is the corresponding phasor for the negative time dependence. So is that true? In order to prove that that's true, what do we need to do? Well, we need to take our phasor, which is the complex conjugate of our original phasor, multiply that by exponential j omega t, take the real part, and then hope that that's equal to our time dependence. And the time dependence in this case is going to be h, let me move that here, it's going to be h cosine and then minus omega t plus phi. So if we can show that this is true, then we're in business, and then the complex conjugate of h is indeed the phasor corresponding to the minus t time dependence here. That's actually a piece of cake to show this. So we need to figure out what the real part of, and then we have the complex conjugate of our original phasor. So we have this is our original phasor. If we now take the complex conjugate, that it basically means replacing phi by minus phi. This is going to be h exponential minus j phi. And then we multiply our time dependence, exponential j omega t. If we do that, then basically Euler's equation tells us that what we have is h cosine omega t minus phi. But luckily, cosine is an even function, and we can also write that as cosine minus omega t plus phi. And this is indeed what we needed to show. So this thing is equal to that thing. So we can get rid of the question mark and indeed conclude that the complex conjugate here is related to the phasor of the negative time dependence. So that already relates the complex conjugate to the negative time dependence. A final thing we can do to explain this in a bit more detail, or to give a slightly different interpretation, is step C, where we're going to look at Bloch modes. So we know if we have a Bloch mode, h, that we can write this as exponential minus kr times a periodic function u of r. So this is a Bloch mode at wave vector k. The question is, what happens if we look at this complex conjugate? So we already know that that's related to time inversion operation. But what happens if we look at the complex conjugate of this expression and try to interpret this as a Bloch mode with a certain wave vector? So pause the video and think about this. Very trivial here. If we take the complex conjugate, we have exponential plus j k r, and then the complex conjugate of our periodic function u of r. And if we compare this thing to that thing, well, we can indeed see that this is again a Bloch mode, big surprise, but this time it's a Bloch mode which has a wave vector, not k, but minus k. So the wave vector in this case is minus k. And if we take a look at the periodic function related to the wave vector minus k is actually the complex conjugate of the original periodic function. So here we have it. If we take a summary of everything that we have found out so far, is basically the following. So as soon as we have a certain solution to Maxwell's equations with omega and k, then automatically we also have a solution for the complex conjugate of that field. And that complex conjugate has the same frequency, the same omega. And we've just figured out that the complex conjugate is related to a Bloch mode that propagates in the negative k direction, the minus k direction. And also we figured out that by looking at what actually that complex conjugate meant in terms of phasors, that is actually a field where the time is replaced from positive t to minus t. So everything ties together nicely. We go from k to minus k, from time to minus time, and that's still a valid solution to Maxwell's equations represented by the complex conjugate operation of the fields.